You are given a spherical shell with radius r that has been covered by some surface charge distribution, some Greek letter, as a function of theta. The potential outside the shell is given by V out as a function of r and theta is equal to c over r squared cosine theta. And the potential inside the shell is given by V in as a function of r and theta, V naught r little r over big R cosine theta. So to solve for C, we set V in equal to V out because V is continuous. And we know that at the surface, R is equal to capital R. So plugging that in, we get the cosines cancel, and we get the R's on the left-hand side of V in cancel. So we get V naught is equal to C over R squared. Solving for C, we get V naught times R squared. So now for B, we have to find the charge density, that little hat Greek letter that's kind of ugly. So it equals the charge over the surface area, which is also, in terms of what we need, is the negative permittivity of free space times the electric field. And thanks to Gauss, we know that the electric field is just the negative gradient of the potential. So solving for the derivative, or the partial derivative of V out, we get V naught R squared over glare, but I think that's R, little r, cosine theta. Then we get, oh, that's wrong. It's supposed to be negative 2 times V naught, oh, there we are. Negative 2 V naught R squared over R cubed. Then, oh, times cosine, yes. Don't forget cosine. So now we're solving for the partial derivative of V in. So it's basically the same thing. So yeah, just get rid of little r. So solving for the distance of the difference of these, we get negative 2 V naught R squared over R cubed cosine theta minus V naught over R, right? I can't see, my big hand's in the way. Yes, big R, cosine theta. And since they're both pretty much the same, by plugging, or at the surface of the sphere, we get negative 3. Yes, we do. Negative 3 V naught over R times cosine theta. And then you move the epsilon naught over. Oh gosh. So slow. You got it? Yeah, epsilon naught times 3 V naught over R cosine theta. So now we need to find the electric field. And thanks to Gauss, we know that the electric field is equal to the negative gradient of the potential. And we have the potential. And we need the inside of the shell, so it's V in. So plugging in for V in, we get the equation that we were given. And you take the derivative of R, which is just 1. And you get that. Now we need to take the derivative, or the partial derivative, in respect to theta, and we just take the equation they gave us. Sine theta is the derivative of cosine, or negative sine theta is the derivative of cosine, and then yeah. Oh my god, I'm going so fast now. So there is no phi, so we know that's 0. So for our E field, we get negative on the outside. Oh, why did I leave it on the outside? But it's V naught over R cosine theta in the R hat direction. And V naught times little r divided by big R sine theta negative. Oh my gosh. Yeah, there you go. And then distributing the negative, we get negative V naught over R cosine theta in the R hat direction, and positive V naught little r over big R sine theta in the theta hat direction, but I didn't write it. So solving for the E field, we need to get it in Cartesian coordinates. So we have what r hat is equal to and theta hat is equal to, so we plug it in. And we get that in the r hat direction, or we get that the r hat x's and y's cancel with each other. And that in the z hat direction, we get negative cosine squared theta, negative sine squared theta is equal to negative 1. So our E field is only going to be z dependent. So our distribution of charges is going to be z dependent and r dependent. So when r is negative, it'll flip the z field. So when it's positive, it's -1, and when it's negative, it's +1. So it's basically that.